Hello, everyone. Welcome to our presentation on how to make solar energy economical. We are Capstone Group 13, and my name is Abishan.
My name is Zach.
My name's Drew.
My name's Wyatt.
The problem we are addressing is how solar energy is currently too expensive. We want to shift to solar panels that produce electricity at a higher efficiency while keeping costs down. We can connect this problem to our local community, which is North Carolina. Reducing the cost of solar panels will help rural areas and low-income groups in North Carolina to afford solar panels. On top of that, solar energy is only a small part of North Carolina's total electricity generation. According to NC State economists, solar energy only accounted for 7% of the total energy generated in North Carolina in 2016. And according to the U.S. Energy Information Administration, as of 2019, North Carolina's nuclear power generation ranked top 10 in the country. These 2 points of data show the solar panels plays a small role in North Carolina's electricity generation, which we want to increase. As you can see on the pie chart from the NC State economist, natural gas and coal make up almost 70% of energy production, whereas renewable energy sources such as solar and hydroelectric only make up around 12% of all energy generated.
So a little history on North Carolina's energy. So while 7% of the total energy generation may seem like a small number, North Carolina has the second highest percentage of solar energy in the nation, only behind California. This astounding growth can be credited to the state's renewable portfolio standard passed in 2007. This portfolio essentially required that by 2020, 12.5% of the total energy sources had to come from renewable energy. By 2019, North Carolina generated about 4,700 megawatts in solar energy and about 3,000 megawatts from hydroelectric power. So as you can see by looking at the graph, solar installations didn't really take off or show up on the graph till 2018 in the residential side of things. So a large majority was used for utility and non-residential. So therefore, by new ideas and designs like ours regarding solar, we should be able to increase the amount of installations in the residential field in the coming future.
We plan to address the problem by making solar panels more efficient, and we can do that by proposing the idea of black silicon cells made from carbon nanotubes. So here are some points of data. Black silicon is able to absorb light at a much higher rate in comparison to normal solar panels, which allows a more efficient energy conversion. In 2011, the utilization of black silicon cells created a world record with an energy conversion rating of 18.2%. And most solar panels today only have an energy conversion rating between 11% and 15%. So this means that black silicon solar panels have a higher energy conversion rating, which is the reason why we're using them. This will also allow rural areas to purchase more solar panels, which increases the use of energy in more places around North Carolina.
So we found this helpful graph that shows that as the price per watt from solar energy decreased, the total gigawatt capacity of solar panels increased. So this means that there has been a positive trend in terms of price dropping and efficiency increasing, which is what we are focused on. So carbon nanotubes. Carbon nanotubes are essentially sheets of single-layered carbon atoms. These nanotubes have a natural tendency to stick together and also chemically bonded together by an sp2 orbital, which is a very strong bond of molecular interaction, a set of hybrid orbitals. By combining both of these aspects, scientists are able to create extremely durable and lightweight material that has a high conductivity of electrical and thermal properties. So to describe these, they would be approximately 400 times stronger than steel, despite having a sixth of the density of steel. They have a higher thermal conductivity of diamond. They are also extremely chemically stable, resisting many chemical reactions unless exposed to higher temperatures and oxygen. So the main premise of our prototype was to test if the color of photovoltaic cell would affect efficiency. Our design consisted of 4 different colors of felts that were laid out in plastic containers on a piece of plywood. Using different colored felts, we would help prove our solution to more efficient solar panels, being that black silicon is a much better choice. The containers were used to simulate similar conditions to real solar panels. Outside variables wouldn't affect the felts and would help give more consistent results. Our testing itself was leaving the plywood out in the sun and measuring the temperatures of felts each hour. So as you can see in the picture, it shows our prototype and how we were designing it. So our design consisted of 4 plastic containers, 4 different pieces of felt, and piece of plywood, and also glue to glue them down. So with these materials, we were able to make a prototype of our design by cutting pieces of felt into the same size as plastic containers and gluing them down onto the piece of plywood so it can be placed outside for testing.
This is our final testing model. And in our final design, we placed the boxes from an equal distance from each other. And we left enough space at the top for 2 additional boxes if we wanted to test more colors. This is our solar panel model. And it consists of a solar panel, an inverter, fuses, battery, and an AC breaker panel. And we created this solar panel design because we wanted to aim to make it more affordable than typical residential and commercial solar panels. So the pricing here is $15 for both of the fuses, the portable battery, which would be $500, a big battery, which would be $5,400, and then the solar cells with carbon nanotubes. And this is priced by the dimensions in the area. And this would be $9 per square meter, 5 cents per watt, and 3 cents per watt for both the manufacturing inverter. So I wanted to compare this with a REC 330 watt model. And this is priced at 46 cents per watt. An example is a 5,000 watt load in a house. The cost of the 330 watt module would be 46 cents per watt. So that'd be 46 cents times 5,000 watts, which is $2,300. And this excludes the price of a battery. So the pricing for the option that we researched is based off of the area in square meters of the solar panel. So the dimensions of the REC 330 watt model is 1.6 meters by 0.99 meters, which would be 1.65 square meters in area. So when you compare this with the REC 330 watt module, given the 5,000 watt home with the estimated 50 feet of wiring, the cost of our solar panel design with one solar panel with an area of 1.65 square meters will be $458.78. This is $14.88 for materials, $250 from manufacturing, $150 for the inverter, $30 for the fuses, and $13.90 for the wiring. And $450.78 is less than $2,300. This is only the cost without a battery and for a home module with only one solar panel. The cost of one solar panel with materials and manufacturing is $264.88 with our design. This means that consumers can buy 6 more solar panels for $1,589, which is still less than the one REC 330 watt module. This cheap price means that solar panels with carbon nanotubes will make solar energy economical. And here's a graph of rally sunlight hours, which helped us to see when would be the best times to use solar panels.
So I did the majority of the testing, so I'll take over from here. Our first test was a morning test on May 4th from 10 a.m. to 12 p.m. The temperature outside had a range from 75 to 84 degrees, and the highest temperature recorded was 179.1 degrees from the black felt at 12 p.m. So the next slide is a graph I made in order to help better visualize some of the data. The colors correspond to the actual color of the felt, and the red step line represents the temperature outside. So our second day of testing was on May 5th and was another morning test from 10 a.m. to 12 p.m. The temperature outside had a range from 72 to 81 degrees, and the black felt once again had the highest temperature of 167.8 degrees at 12 p.m. And then here's another graph for all the data to help better visualize it. So our final test was an afternoon test from 1 to 3 p.m. on May 13th. The temperature range outside was from 66 to 70 degrees, with the black felt again recording the highest temperature at 180.7 degrees. And then here's the final graph that shows that day. Unfortunately, we couldn't get a day 4 testing in the afternoon because of inconsistent weather. We didn't have 3 solid straight hours of sunlight, so we only had one afternoon test. So our testing conclusion is that the time of day, the temperature outside didn't change the fact that the black felt always recorded the highest temperature, and that the darker shades of blue consistently had a higher temperature than the lighter shades of blue. And after numerous testing days, we reached the conclusion that black has the highest light absorption out of all the colors. Therefore, using black carbon nanotube cells would be much more efficient than the standard dark blue silicon cells.
And how does our research solve the grand engineering challenge? To recap, make solar energy economical is the grand engineering challenge that our project is aiming to solve. The most optimized solution that we found for this grand engineering challenge is cheaper solar panels with higher efficiency and cheap generation. We also look into the technical details of solar panels, like which materials and colors would decrease the cost and increase the efficiency and light absorption of our solar panels. Through our research, we found that a solar panel design with black photovoltaic cells made of carbon nanotubes is the most fitting of the criteria for the solution.
Thanks for listening to our presentation. We hope that what you can take away from our presentation is North Carolina is on the right track when it comes to renewable energy, specifically solar, but there is much room for improvement.